Hi students, in this video we're going to cover the calculus of vector value functions. That means that we're going to derive vector functions, integrate vector functions, and discuss the unit tangent vector. So all of our basic derivative rules that we learned in first semester and second semester calculus are going to apply to vector functions. That means that we can derive them, that means we can integrate them. If we have a vector function that has the components xt, yt, and zt, then the derivative of that vector function is x prime, y prime, this should be a prime, excuse me, make this a prime, and z prime of t. You may also see this as f of t, g of t, and h of t. And that's just going to mean that we still have the derivatives of each one of those components. But again, the letters are just placeholders. This derivative is called a tangent vector provided the tangent vector isn't the zero vector, because then we don't actually have a place of tangency, and it's going to be, we'll see what happens when we get to that point. So for our first example, we want to find the derivative of RT. So first off, we may see RT occasionally written in unit vector form. So that would be if we had something like t squared I plus tj plus sine t k. That would be the unit vector form for this. For my purposes, I would strongly prefer the component form. It gives us the same information and we just write less. So our derivative is going to be the derivative of t squared, which is 2t, the derivative of t, which is 1, and the derivative of sine t, which is cosine t. Very straightforward. Next, we have the unit tangent vector. So just like all unit vectors, to get the unit vector, you take the vector and divide by its magnitude. Now for a vector function, that's going to change based upon what the value of t is, but it has the same general concept. We're going to take the vector, divide by its magnitude, and we're going to get this special function called the unit tangent vector. And it has this notation, which is just the derivative divided by the magnitude of the derivative. So for our second example, we want to find the unit tangent vector, and we also want to evaluate this vector as t equals pi over 2. Those are separate things. So first, we need our derivative. So r prime of t is, all right, so now we have to do the chain rule. Remember chain rule, derivative of the outside function times the inside. So our outside function is cosine. So the derivative of cosine is negative sine, keep the angle, so negative sine 2t, but then we multiply by the derivative of 2t, which is 2, so we get negative 2 sine 2t. The derivative of 5 is 0, and the derivative of 3 sine 2t is going to be 6 cosine 2t. So we'll do the second part first. If we evaluate this at pi over 2, we're going to get negative 2 times the sine of pi, 0, and 6 times the cosine of pi. And that is going to give us the vector that is 0, 0, and 6 times negative 1 is going to be negative 6. So that's the vector evaluated at that point. Now, if we find our unit tangent vector, we're going to get, all right, so we already have our derivative. So now we need the magnitude of the tangent vector. We need the magnitude of r prime. So that's going to be, just like we always know, the square root of negative 2 sine 2t squared plus 0 squared plus 6 cosine 2t squared, which is going to equal the square root of, all right, so negative 2 sine 2t squared is going to be 4 sine squared t plus 0 plus 36 cosine squared 2t. I'm sorry, that should be a 2t right there. So 4 sine squared 2t plus 36 cosine squared 2t. And so we're going to do this a lot when we deal with unit tangent vectors. We can split this to be the square root of 4 sine squared 2t plus 4 cosine squared 2t plus 32 cosine squared 2t. And here we know that sine squared plus cosine squared is equal to 1. So 4 sine squared plus 4 cosine squared is going to be 4. So this is going to simplify to be the square root of 4 plus 32 cosine squared 2t. And if we keep going, we can factor a 4 out of the square root, which means that we would get 2 times the square root of, so we took a 4 out, so that's going to be 1 plus 8 cosine squared 2t. So our unit tangent vector, we would have t of t is equal to, so we're going to write this in component form. We're going to have, our components are negative 2 sine 2t, 0, and 6 cosine 2t, all divided by 2 times the square root of 1 plus 8 cosine squared t. I'm sorry, 2t, my apologies. So if we go back and check, so we already know that at pi over 2, we get a vector that's 0, 0, negative 6. And if we substitute it in pi over 2, we should be able to get a unit tangent vector. So let's see what happens if we substitute in pi over 2 here. So t of pi over 2. So in the numerator, we already know that we're going to get the vector 0, 0, negative 6. In our denominator, we're going to substitute in pi over 2. So this angle is going to turn into pi. So the cosine of pi is negative 1. Negative 1 squared is 1. 1 times 8 is 8. Plus 1 is 9. The square root of 9 is 3. 3 times 2 is 6. So what we get is a vector that has the components 0, 0, negative 1. So, of course, the magnitude of that vector is 1. So we can see that this unit tangent vector actually gives us a unit vector when we substitute in a particular value. So next, the product rule, quotient rule, and chain rule are valid for finding the derivatives of vector functions. We also now have a unit, we also have a dot product rule and a cross product rule. So if u and v are functions in terms of t, then the derivative of the dot product is the derivative of the dot product of the derivative of one function times the second function held constant plus the second function held constant and the dot product of the second function held constant times the derivative of the first function. Notationally, it looks like what I'm putting a brace under. So it's the product rule, but with the dot product applied to it. And similarly, we have the cross product rule. The order in which you do the cross product will matter. So remember, if we have v and v prime on the left, we get the negatives of those cross products. So again, the order is going to matter. So for example 3, we have u is, you see what u is and you see what v is. We want to find the the derivative of the dot product and the derivative of the cross product. So first, we know that u dot v prime is equal to u prime dot v plus u dot v prime. So let's see. Well, u prime is going to be, if we want to write this in component form, that's t squared negative cosine 2t and e to the t squared. And v is going to equal cosine t sine t and negative 1. So u prime is going to be, we're just going to write this out as a vector. So 2t, the derivative of negative cosine 2t is going to be 2 sine 2t, and the derivative of e to the t squared is 2t e to the t squared. Chain rule, remember. So all of this is our u prime. And then if we multiply this by v, we would get, what is v? Cosine t. So we're just doing the dot product of that, and cosine t sine t, sine t and negative 1. So u prime, this part is v, and then we're going to add, all right, so now we need u, so u is t squared negative cosine 2t and e to the t squared, and we multiply by the derivatives of v, so it's going to be negative sine t, cosine t, and 0. So if we were to actually write out our dot product, that would be 2t. So remember, dot product is, let's color code this. So 2t cosine t. So 2t cosine t, and then different color. Let's go with this blue. So then 2 sine 2t times sine t is going to be 2 sine t sine 2t. Oh, I'm sorry, we're adding. And then minus, so then minus 2t, minus 2t e to the t squared. So that takes care of that first dot product. And then for the next one, we have t squared negative sine t. So minus t squared sine t. Yellow, I guess, is next. And so then we have cosine t and negative cosine 2t. So minus cosine 2t cosine t and the plus 0 part. So that's it. Like if t was a value, if t was some number, we're going to get a scalar, because all of those are going to turn into numbers. So we could have also done the dot product and then have done the product rule for each term. It's the same amount of work. And next we have the cross product rule. So here I'm going to say just do the we'll do the cross product and then do the derivative. So let's put in table form, and this is going to look crazy. Yeah, it's easier to do it this way. So we're going to have I, J, and K, and we may run out of room. My apologies if we do. I actually need more space. So let's get a little bit more space here. So, and write this closer to this other function. So let's block out some room. So we're going to have I, J, and K. And so I is t squared negative cosine 2t and e to the t squared. And v is cosine t sine t and negative 1. So our cross product, so we're going to say nope. So we'll put it up here. U cross V is going to equal negative cosine 2t. Man, this is going to be crazy. So negative cosine 2t e to the t squared sine t negative 1 times I. And then minus for j, we're going to get t squared e to the t squared cosine t and negative 1 j, and then plus for k, we're going to get t squared negative cosine 2t cosine t and sine t. So if we multiply this out, we're going to get cosine 2t minus e to the t squared sine t I minus negative t squared minus e to the t squared cosine t, excuse me, j and plus t squared t squared sine t squared sine t plus cosine t cosine 2t k. And we still have to actually do the derivatives of that. So we'll write that in blue. And it's just calculus. It's just long. So we're going to say u cross v prime is equal to, for that first term, the derivative of cosine 2t is negative 2 sine 2t minus the derivative of e to the t squared sine t. So that's going to be 2t e to the t squared sine t plus cosine t times e to the t squared. And all of that is I. And so then minus for the next thing, we're going to get negative 2t minus 2t e to the t squared plus e to the t squared sine t for j, and then for k plus 2t sine t plus t squared cosine t, and then have to write the rest down here. So then minus sine t cosine 2t minus 2 cosine t sine 2t, and all of that is multiplied by k. So you can see for the cross product, the derivative is quite long. I won't ask you to do anything that's crazy in class, but it illustrates the point. So for antiderivatives, remember the antiderivative of a function is not unique. Up to a constant is unique, but to find the antiderivative of a vector function, we're going to find the antiderivative, which means we integrate each component. So for our next example, we have r prime of t is 2 sine 4t cosine 2t and e to the 2t. So we're going to say r of t is equal to the antiderivative of this vector function. So 2 sine 4t cosine 2t and e to the 2t, excuse me, dt. So the antiderivative of sine 4t, so let's quickly review some antiderivative rules. The antiderivative of sine of some number times, we'll say t in this case, is negative cosine of that number times t divided by that number. And something similar is going to hold up for cosine. The antiderivative of cosine of some number in t is equal to the sine of that number in t divided by that number plus a constant. And similarly, the antiderivative of e to some number in t is equal to e to that number in t divided by that number. Cool. So here we're going to get negative 2 cosine 4t divided by 4. We'll write this in component form. And then we're going to get sine 2t divided by 2 and e to the 2t divided by 2. And like I said, up to a constant. So we'll say plus C1 plus C2 and C3. So obviously we can simplify, and we could put this in one single component. So we could get negative cosine 4t over 2 plus C1, comma, sine 2t over 2 plus C2, and e to the 2t over 2 plus C3. And that is our antiderivative. Again, not unique because we don't have any initial value conditions. Now, for example, 5, we have to determine the specific vector function that produces the derivative, and it's this derivative. So first, we're just going to write RT and individually do the antiderivatives. So the antiderivative of e to the t is e to the t. The antiderivative of, all right, so here, the antiderivative of the square root of t is the same as t to the 1/2. Remember, you add 1 to the exponent and divide by the exponent, so that's going to be 2/3 t to the 3/2. And the antiderivative of dt over t is the ln of t. So let's remember that. So we're going to get here for the second component 2/3 t to the 3/2, and the antiderivative of 1 over t is the ln of t. And again, plus, we know C1, C2, C3. Now we have this initial condition that when t is 0, we should get whatever points. So, well, we should get the point 0.025. So r of 0 is going to equal e to the 0, 2/3 0 to the 3/2. And actually, I meant for this to be r of 1 because the ln of 0 is undefined. Excuse me, change this to be a 1. It's going to change our workaround a bit. So to the 1, so we're going to have e to the first, 2/3 times 1 to the 3/2, and the ln of 1, plus then C1, C2, and C3. So what that's going to mean is that for our first component, it's going to be true that e plus C1 is equal to 0. Then that's going to imply that C1 equals negative e. Next is going to imply that 2/3 plus C2 equals 2. So C2 is equal to 2 minus 2/3. So C2 is equal to 4/3. And last, the ln of 1, which is 0. So 0 plus C3 equals 5 is going to obviously imply that C3 equals 5. So our specific function that meets this criteria is RT is equal to e to the t minus e. Where was I? So 2/3, not e, t, 2/3 t to the 3/2 plus 4/3, and the ln of t plus 5. So if you go back and check, if you substitute in 1, you're indeed going to get the point 0, 2, and 5. And for our last example, we have finding the definite integral of this function. So we're going to write this in component form. So the antiderivative of the first component, we'll call this r prime of t. Actually, we'll leave it on. So we'll say r of t is going to equal, the antiderivative of t squared is 1/3 t cubed. We're going to write it in component form though. So t cubed over 3, the antiderivative of 2t is just t squared. And the antiderivative of negative pi cosine pi over 2 is, that should be add a t in here. My apologies. That should be a t right there. Pi over 2t is going to be, all right, so we're going to get pi, well, negative pi sine pi over 2, and then we divide by pi over 2 and multiply by 2 over pi. So we'll say times 2 all over pi, and that actually simplifies for us a bit. So we get t cubed over 3, t squared, and just negative 2 sine pi over 2, and we want to evaluate that from 1 to 3. So remember, for a definite integral, this is going to equal r of 3 minus r of 1. So it's just two vectors subtracted. So r of 3 is going to equal 3 cubed over 3, 3 squared, and negative 2 sine, this should be a t, so negative sine 3 pi over 2. That should be a t there too, my apologies. And that simplifies to be 27 divided by 3 is 9, so 9, 9, the sine of 3 pi over 2 is negative 1, so times negative 2 is 2, and r of 1 is equal to 1/3, 1, and the sine of pi over 2 is 1, so times negative 2 is negative 2. So r of 3 minus r of 1 is equal to 9 minus 1/3, 1 minus 9, and 2 minus negative 2, which is going to equal 26/3, negative 8, and 4. So all of the things that we've done in Calculus 1 and Calculus 2 are now going to carry forward for vector functions. All right, so that concludes this video of calculus with vector functions. We did derivatives of vector functions. We found the unit tangent for a vector function. We found the dot and cross product rules for a vector function, and we did antiteratives with vector functions. See y'all in class.